Optical fibers transmit data over long distance at high speed using flexible, transparent glass or plastic. They rely on total internal reflection and consist of a core, cladding, and protective coating. Commonly used for Internet cables, they offer high bandwidth, low signal loss, and immunity to electromagnetic interference. Beyond communication, optical fibers are used in lighting, imaging, sensors, and laser. In the oil and gas industry, spanning upstream, midstream, and downstream operation, optical fibers enable reliable, high-speed data transmission essential for efficient exploration, extraction, refining, and transportation. What is the basic principle of optical fiber? Optical fiber use the total internal reflection phenomenon, which happens when light travels from a dense to a rare medium at an angle that is larger than the critical angle. Optical fiber have transparent glass or plastic and comprise three elements: the core, through which light passes, the cladding, which is of lower refractive index to reflect light back to the core, and the protective layer that provides support to the optical fiber. The light entering the core at the correct angle is repeatedly reflected, ensuring the light can travel a long distance without losses. Optical fibers support high speed and high bandwidth for data transmission and do not experience any electromagnetic interference. These benefits make optical fiber commonly used in communication devices, the internet, sensors, and industry.
Now, we will cover why these fibers are critical in oil and gas industry. Number 1, they survive where others fail. We are talking about extreme heat, insane pressure, hydrogen exposure, and corrosive chemicals. Electrical sensors would throw in the towel in these conditions, but optical fibers, they just keep going. Next, safety. Optical fibers are non-conductive, so there are no sparks in explosive areas. Bonus, they are immune to electromagnetic interference, meaning your data stays accurate and reliable. In oil and gas, reliability is not just nice to have, it is critical. And finally, they are cost-effective in the long run. Sure, they might cost a bit more upfront, but they minimize downtime through continuous monitoring and support high bandwidth, SCADA integration. Less downtime, fewer headaches, and more money saved. Win-win. So now that we know why we need them, let's move on to the fun part, the types of optical fibers used in oil and gas and what each one does. First up, single mode fiber, SMF. Think of it as a narrow, high-speed highway for light. Only one path of light can travel through, which means low signal loss and super high bandwidth, perfect for distributed acoustic sensing and long-distance pipeline monitoring. Basically, anywhere signals need to travel dozens of kilometers without repeaters. Next, multi-mode fiber, MMF. Now, imagine a multi-lane highway for light. Multiple paths travel simultaneously, which is great for short distances but can get messy over long runs because of signal blurring or model dispersion. MMF is ideal for distributed temperature sensing in single well bores or refineries, where capturing more backscattered light is key. Then we have specialty fibers. These are the tough guys, designed for environments that would destroy normal glass. Some examples: hydrogen-resistant fibers stop hydrogen from entering the glass and darkening it. High-temperature coatings like polyimide or even metals like copper can survive downhole temperatures over 300 degrees Celsius. They are used for permanent downhole monitoring in high-pressure, high-temperature reservoirs. Basically, when the environment is extreme, specialty fibers don't blink. Finally, the hybrid sensing fiber, multiple fiber types in one cable. This lets you do multimodal sensing, one fiber for acoustic data, another for temperature, and maybe a third for high-speed data. Perfect for smart wells, giving a 3D real-time view of the reservoir, one cable, multiple insights. Now, Let's look at how optical fiber is actually used in the oil and gas industry. First is distributed temperature sensing, or DTS. DTS allows engineers to see a complete heat map of a well or pipeline. Instead of measuring temperature at one point, it monitors temperature continuously along the entire fiber. As light travels through the fiber, changes in temperature affect how the light reflects. The system uses this to calculate the exact temperature at every point along the cable. DTS is important for flow assurance, especially in deep-sea pipelines where oil can cool down and form wax. It also helps with leak detection because gas leaks cause sudden cooling due to the Joule-Thomson effect, which DTS can quickly detect and locate. Next is distributed acoustic sensing, or DAS. DAS turns a single fiber optic cable into thousands of highly sensitive microphones. It works by detecting tiny vibrations caused by sound. These vibrations slightly strain the fiber, and by measuring how the strain affects the light inside the cable, the system can essentially hear what is happening nearby. In oil wells, DAS is used for downhole monitoring, where it listens to oil and gas flowing into the well and helps identify high-producing zones. DAS is also used in seismic surveys, where existing seabed fiber cables can detect vibrations from natural or man-made sources to help locate underground oil reservoirs. The third application is pipeline monitoring, which combines DTS and DAS. DAS can detect third-party intrusions like digging near a pipeline, while DTS and strain sensing help monitor the structural integrity of the pipe. This provides early warnings before serious damage happens. Optical fiber is also used for pipeline inspection gauge. Peak tracking. Peak tracking is a way to locate and follow a cleaning or inspection tool inside a pipeline by listening to the sound of the inspection tools moving inside the pipeline. Operators always know exactly where the peg is, even across long distances.
Now I will explain the advantages of optical fiber in the oil and gas industry. First, optical fiber allows continuous monitoring along all wells and pipelines because the entire length of the cable can act as a sensor, making it suitable for long-distance monitoring. Second, optical fiber is immune to electromagnetic interference and does not conduct electricity, which makes it safer for use in oil rigs, refineries, and offshore platforms. Third, optical fiber has high sensitivity for downhole and reservoir monitoring, allowing small changes in temperature, pressure, or strain to be detected accurately. Another advantage is real-time monitoring through permanent installation, which enables operators to continuously monitor well conditions and detect problems immediately during operations. Lastly, optical fiber allows early detection of pipeline leaks and failures, helping operators shut down pipelines quickly to prevent major spills and environmental damage. Although fiber optic sensors provide continuous and accurate monitoring for oil and gas pipelines, there are several challenges and limitations. One major challenge is installation and retrofitting of underground pipelines in oil and gas operations. Installing fiber optic sensors on existing underground pipelines often requires digging to reach the pipeline, making large-scale deployment costly and time-consuming. Next, long-distance pipeline monitoring oil and gas pipelines can extend over hundreds of kilometers, where signal weakening and interrogator placement become major challenges for reliable monitoring. Data interpretation and integration. Interpreting fiber optic sensing data in oil and gas pipelines is complex and lacks standardized methods, making integration into existing monitoring systems complex. There are also limitations such as strain transfer and bonding reliability. Accurate strain monitoring in oil and gas pipelines depends on effective bonding between the fiber and the pipeline, which may degrade over time and reduce data accuracy. Performance in harsh operating environments. Oil and gas environments such as offshore platforms buried pipelines, and non-pressurized systems expose sensors to corrosion, biofueling, and variable conditions that can limit their performance. Finally, sensor technology trade-offs, where different fiber optic sensing technologies used in oil and gas monitoring involve trade-offs between spatial resolution, sensing range, and sampling rate.
In conclusion, optical fiber technology significantly enhances efficiency, safety, and reliability in the oil and gas industry. Its ability to transmit real-time data over long distance, resist electromagnetic interference, and operate in harsh environments make it ideal for monitoring wells, pipelines, and reservoirs. By enabling early detection of leaks and equipment failures, optical fiber systems reduce risk, downtime, and cost, supporting safer and more sustainable industry operations.